Okay, so I'll be explaining problem D, inconvenient pairs. So what does the problem say? You are given a grid, and the grid size, like the coordinates of the grid are from 0, 0 to 10 ki power 6 to 10 ki power 6. This grid consists of roads. So, and these roads are vertical and horizontal. So first, I think you are given these vertical roads, and you are given the x coordinates of these roads. Suppose this is at point 5, 0, and this point would be 10 to the power 5, 10 to the power 6. So you are only given this x coordinate for vertical roads, and you have a road like this. Suppose this road has a coordinate of 11, 0. Then you are given roads which are horizontal. Suppose this road is at x0 by 2, this is at 0, 7, this is at 0, 11. So this is the data about the roads. And what else you are given? You have some people, and each person, for every person, you are given his x coordinate and y coordinate, and these persons are initially on some streets. So suppose there can be a guy here, there can be some other guy here, someone else here. So these are all these streets, and suppose there's a guy here. What do you want to find out? You want to find all those pairs, all those pairs of people, such that uh, uh, the shortest distance to meet them is greater than the Manhattan distance between them. So I'll explain this statement. Suppose you talk about this person, uh, and one second. If you're talking about this guy and this guy, what is the shortest distance between them if they travel by streets? So it's obviously this. He travels this much in the y coordinate and this much in the x coordinate. This is same as the Manhattan distance between them. So the Manhattan distance is this plus this. So these guys are not the pair that we are talking about. We are talking about some other guys. Similarly, if you would have picked this guy and this guy, or this guy and this guy, they would not be the pairs that we want to count. What we want to count are people like these two. What's special about them is the Manhattan distances. If I want to go from here to here, I would travel this much in vertical and this much in horizontal. But the shortest distance is either something like this or something like this or something like this. So you can see the y coordinate is same as the Manhattan distance, but the x, but the horizontal distance is more because I'm traveling some distance here, some this part I'm also traveling. So in this case, these are the pairs that we are talking about, and we want to count all such pairs. Also, the number of people is around 2 into 10 to the power 5, so you cannot do a brute force algorithm or something like that. So how do we solve it? The first observation is, like, first thing that we need to think about, uh, when is a pair inconvenience? Inconvenient. So now these pairs of people, these two guys are said to have an inconvenient pair. So when is a pair inconvenient? So first we will talk about this. Suppose we have two guys. We have one guy over here and we have one guy over here. The Manhattan distance between them is something like this. So Suppose that between them, between suppose that initially they are, this guy is in a vertical street and this guy is initially residing in a horizontal street. Sorry, this one is a horizontal street, this one is a vertical street. Or vice versa. This one is in a vertical street and this one is in a vertical street and this guy is in a horizontal street. Like let's say these two people. So this one is in a vertical, this one is in a horizontal. In that case, the Manhattan distance is same as the shortest distance, because you can like go like this, you can also go like this. So if they belong to these different types of street, one belongs to horizontal and one belongs to vertical, then we don't need to worry about them. Okay, so that leaves out the other case, that both of them are on the same type of street. So this guy is here and the other guy, of course the other guy is not going to be on the same horizontal street, because in that case, or in the same vertical street, because in that case the Manhattan distance is same as the shortest distance. So let's consider the other guy to be somewhere here. Now there are, now how am I supposed to reach from here to here? I need a vertical road, okay, to reach from here to here. What can be the possible positions of these roads? The first position can be this, like let's say this in between them. So in between them there is a vertical road. In that case, this is the Manhattan distance as well as the shortest distance. So this is a convenient pair, not an inconvenient pair. What can be the second case? Well, the second case can be that the street is somewhere to the left of both of them, like here. So this will make an inconvenient pair. There is no street between them, no vertically passing street between them. The only vertically passing street is to the left of both of them. So you would have to go something like this, or even if it is to the right of both of them, then also they would have to go something like this. So in both of these cases, the pair is an inconvenient pair. So what we have to do, like what is the gist of the algorithm? Suppose you have this grid and these are the roads. Okay, suppose these are the roads. And there are people like here, 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 here. So basically, there are also people, let's say, on the vertical streets, but let's consider I'm just taking the case of people on the horizontal streets for now. Suppose this is the grid. How would I find my answer? Basically, this thing which I talked about. So first I will look at roads, horizontal roads. First I will talk about these horizontal roads. And I'll pick any two of them. Suppose I pick these two roads. In these two roads, these guys and these guys, if I map them, they will form an inconvenient pair. Why? Because to the left of them, it's also given that 0, 0 is a road. So this is also a road at the end, and there's also a road at the end. Also, the 1e⁶ is also a road. So for these two pairs of people, the vertical roads are to the right, like right of both of them, and to the left of both of them. So this guy would form an inconvenient pair with this guy. This guy would form an inconvenient pair with this guy. This guy would form an inconvenient pair with this guy. The same will go for these two roads. So for each road, the algorithm will be something like not the optimized algorithm, but for each um, so basically for each let's say yeah let's say for each of these vertical roads, for each of these vertical roads, find out all the elements which lie between them, strictly between them. So these two vertical roads, these guys lie. Okay, so there are currently um, five five people here. So five. If I do something like 5C2, if I that is pick any two of them, if I suppose pick any two of them, if I pick these two guys, or I can pick these two guys, so they will form an inconvenient pair. But from this, I would have to subtract something. Since these three people which are on the same horizontal line will not form any inconvenient pair with each other, so I'll have to subtract 3C2 from here. Then I would I would talk about these two pair of vertical roads. I will do a binary search. See, I can sort my guys by the x coordinates initially. So I will see, okay, in between them, how many elements lie. So these four elements lie actually. Four elements lie. So I can do something like 4C2, that is pick any two of them and consider them to be an inconvenient pair and subtract from them those people which lie like basically um, 2C2 in this case. For this road basically there are two people and I have to subtract pairing of them because in this 4C2 I have also paired these two guys. Third case I'll take a little bigger. Suppose I have three people here, two people here and three people here again. So look between these two pair of vertical roads, do a binary search. There are six, eight people. So 8C2 minus these guys 3C2 plus 2C2, that is these guys, because their pairing is convenient, right? We have to subtract that and plus 3C2 again. And for this, the answer would be simply 3C2 for between these two roads. So that would be the algorithm for when you are traversing between two vertical roads. You have to do the same thing for horizontal roads. If you want me to show, I can show you. Um, Suppose let's just take a small example. And there are people here. Here. Since there's a road at 0 and there's also a road at 1 e power 6 which they have given. So look between, now iterate over horizontal rows, and when you're at the ith horizontal road, look at I and I plus 1, these two roads, sort all my people by the y-axis and find the count of people lying in this range. Suppose this is y is 0, here y is 5. So your range will be 1 to 4. Okay? And I don't want elements which are lying here. I want elements which are lying strictly between them. So there are total 5 elements. So 5C2 minus these pairings. These 3C2 plus 2C2. And similarly you can go. This is the gist of the algorithm. Now what is easy and what is tough to calculate here. See, whenever you are traversing in this, let's talk about the complexity first. Suppose there are n vertical roads and m horizontal roads. There are k people. So when you traverse over these vertical roads, it would be a complexity of n, and every time you're also doing something like a binary search. Like when I'm between these two roads, I have sorted all of my people by x-axis coordinate, and I am finding the people in this range. So it would be n log k. Apart from that, I also need to know that, in this particular row there are three guys when I am subtracting. In this row there is only one guy. In this region there is only how do I put it? Three guys. I also need to know about that. So how do I find that out? And now how do I find that out? So uh, what I'll do is I will do this subtraction, of 3c2, 2c2, this subtraction at the very end. At the very end. First of all, I'll just sum up these values, 5c2, 4c2, 8c2, 3c2, because these are simple to find. You only need to do a simple binary search, and okay, between these two x coordinates there are 5 elements. Between this and this x coordinate there are between these two x coordinate exclusive there are 4 elements. There are 8 elements and 3 elements. So you can do a binary search, and that would cost you a complexity of n log k. Similarly, when you iterate over the horizontal roads, that would cost you a complexity of m log k. Now I need to basically do this subtraction step. So let's first see, overall, what are we subtracting? What are we subtracting? So this time I'll draw, let's say I draw roads like with red color. So these are my roads. Suppose the roads don't have any width, like I'm showing roads with some width. That was only for explanation, but the roads don't have any width. So this is the road at suppose the 0th x coordinate. This is the road at 5th x coordinate, 8th and 1 e to the power 6. This is the road at 0, 2, 3, 5 and 1 e to the power 6, the y coordinate. Suppose and the elements are like these. In between the roads. Also we'll also take these elements. So I'm merging the two cases which I showed separately. So what are we actually subtracting is answer minus 1c2, like the number of elements in this section. Then the number of elements in this section, which is again 1c2. Then the number of elements in this section, which is 2c2. Number of elements in this section, 3c2. Number of elements in this section, 2c2, and so on. So how do I do it? What I have done in my case is I iterate over these. Basically, I first of all create a map, which I call it as horizontal map. So basically, it stores these horizontal lines. So for this line, suppose the line at the 0th y coordinate, I am storing a map which contains these elements. Then for the y coordinate 2, I am storing a map which contains these 5 elements. This and this. Similarly, vertically I am also storing. For example, if this is suppose x-axis 8, so I also create another map. The operations for both the map are same. So I create another map which I called as vertical map, let's say. And for 8 x-axis, I am storing this element, this element, this element, and this element. So I am storing 4 elements here. Then what I do is I sort all of my maps. So basically all the elements are sorted by their x coordinates in this case, and in this case by their y coordinates. Now how do I solve? So I'll take an example of a single line. Okay, let's talk about this line at the y0 coordinate, and we have elements here, elements here. Let's say I have elements like this on this line. What I do is I come to this element and I try to find, there's also a horizontal line here. Suppose the x coordinates are 0, 8, 12, 13 and 1 e to the power 6. Also let's take elements at these intersections points as well. Okay. So when I come to this element for my horizontal map at the y0, I try to find the previous or the closest vertical line. Okay, how do I do that? I all these vertical lines coordinates I've also stored. So I have made an array which I call as vertical positions, let's say, which contains these elements 0, 8, 12, 13 and 1 e to the power 6. So you can start from this or you can also start with this. What I have maintained is a previous closest line element which I have initialized at 0, and I have also maintained a current previous line which is for the element I am on. So for this element the current previous line is 0. Okay, since this is the first element, you can just go on, you can move forward. Okay, when you are moving forward you will set your previous line as the uh, current previous line. So previous line would be 0 and now you are at this point. You also maintain a counter element. So counter is initialized with 1 since I am here. Like I'm just trying to explain the gist of it. Now I'm at this element. I try to find what is the previous closest line. This element also has that previous closest line of 0. If this element also has a previous closest line of 0 and this element also has the same, that means they are part of the same section. But take example this element and this element. This element has a previous closest line of 8 and this has a closest line of 0. So these two are not part of the same segment. So whenever you face a condition like, okay, this x is not similar to this x, they are a part of different segments. So you can, at this point your counter would have been 2 and from answer you would have subtracted 2c2. 2 why 2? Because these two elements are in the same segment. Then once you suppose go to this point, you say okay, this element and this element belong to different segments. So from answer I'll also remove 1c2. 1c2 is basically 0 and why 1? Because in this segment there were one element. Then okay, I move to this element. These two have the same, like 12 as your previous line, so my counter is 2. And this one also has the same, counter would be 3. This one lies, like this one has a previous line of 13 basically. So okay, at this point I'm going to subtract 3c2 from answer. And these elements which are at intersections, basically I also made a special check for that. If an element is at an intersection, then basically ignore that element, make your previous line as 13 in this case and move to the next element, and then you are here, you would subtract 1c2, and you would do that for all of your um, horizontal lines and for your vertical lines. So basically why I have done this algorithm, I need a way to find how many elements lies in such segments. And you can do some other method if you, because my code was very long. Uh, but basically, if you know any other way to do this check efficiently, then you can also do that. I hope you understood a little bit about the problem. That's all for this video. Thank you for watching. Bye.